Okay, so good morning. In the last class, we started discussion about linear classifiers. What did we discuss in that in the previous class? The equation of the linear classification itself we have discussed. We discussed it in terms of the discriminant equation, that you discriminant function, rather we will call it as a discriminant function, which is g of x bar is equal to w bar transpose times x bar plus w naught. And then we have seen what would be the linear hyperplane that you would get, its relationships with respect to these weights, its relationship with respect to its orientation, its relationship on where exactly this line will be placed, the value of Euclidean distance to a given point x bar from this plane, and the distance from origin, the Euclidean distance from the origin to this plane, and of course the value of this function for a properly classified two classes where we have done. These are all the things that we have discussed in the previous class, right? And we in fact derived the expressions also for r, which gives you the Euclidean distance, and then we have also derived the expression for distance from the origin to the line. These are the things we discussed. And we have also seen that g of x bar, once you do a linear classification, assume that this is your class omega 1, omega 2. For one it would be greater than 0 and another it would be less than 0. So that also we have discussed that. Now, if you look at the subsequent mathematics that you would see there is one mathematical hack or trick that people typically do, and we will also do, is to write it as simply a linear system. What does that mean? Is this not being having the background in electrical engineering and signal processing? You should be able to comment on, is this a linear system? Suppose I have a system like this. Is this a linear system? What is it that is making it not a linear system? Yes, this W naught is what it is making it not a linear system or a non-linear system. Is there any way that you could make it linear?
W naught can come into the last.
Okay, so let us follow what he has suggested. That's the right approach to go. Let me call those weights now as A bar, where I would keep W1, W2. Let's say it's an L dimensional feature vector is what I am considering. So I have WL here. So the idea is to keep W naught here. Then what will you do?
And making the last value of the x vector.
Very good. So x bar will be equal to now x1, x2, and it will be there till xl. What will you take here? 1. Good. See, this is what is essentially you are doing here. Can you tell me in terms of slightly rephrase your statement and tell me what exactly has happened now? So let us first, maybe I'll write the equation first. Okay. So yeah, let me not write it as x bar because this is x bar and there is a confusion here. So I will instead write it as y bar. Tell me first the equation here. What is the equation now? The new equation? G of y bar is equal to A bar transpose times y bar. Correct? Can you comment on that or rephrase or tell me what exactly have we done here? In terms of vector space, you tell me. That's right. From an L dimensional space, you have now moved to an L plus 1 dimensional space. one space higher. This is, for example, now L plus 1 cross 1 vector. Similarly, this is also L plus 1 vector of size L plus 1. So if you look at in L dimensional space, this is nonlinear. You are moving into an L plus 1 dimensional space, and this makes it linear. See, it will be convenient for us because from now onwards, you don't have to deal with two terms here. You just treat it with just this term itself. Okay. Assume that if your line, your decision plane itself is passing through the origin, anyway, there is no issue. In those cases, it is anyway just W bar transpose times X bar. Even if it is the other way around, if you just instead of an L dimensional space, if you go to L plus 1 dimensional space, that will still give you this equation. So what we will do from now on is we will just, our equation will be from now onwards will be simply this. I could have used Y bar here and again A bar here, but that's okay. Hope this is clear. It's just matter of interchanging the variables. But now on, I will use this itself for all our analysis. But don't mistake not that we are dealing with only planes that are passing through the origin. It is just even if it is passing through the origin, if my original feature vector, you consider it as something an L dimensional space, and then my X bar is those L dimensional plus 1 is my X bar. Okay, treat it that way. It's just matter of convenience, since that we got used to and attach it to an extent to W bar and X bar. I still use it, but never confuse it with just exclusively to only to those lines that pass through origin. This can indeed represent the planes that are not passing through origin as well. Is this point clear? Everyone clear with that? Okay, good. What is our objective now? We managed to get an equation for this line, but we have to somehow find this line now. So what all that we have? Assume that you are given some feature vectors x1 and x2. You have these points. Now you have to find out a line that separates these two things, so that later when you get a new test sample, you will substitute it there and see, you will assign simply to which class it belongs. But it is from the training data set, you have to figure out this line. Any ideas on how we should approach from here? Okay, good. This is also covered to an extent in DLIP. Okay, good. And then what? Right. So maybe we will go a little more detail now. That's overall, that is correct. That's what we will be doing it. A couple of assumptions let me write here with which we are starting. One is regarding this linear classification. What is this assumption is, a linear decision plane will be able to classify or separate or distinguish two classes. That's my first assumption. Second assumption is there are no outliers or anything like that. So suppose it will perfectly fit there. You may keep it in this assumption itself. I don't want to write two assumptions. You just linear classifier is such that it will nicely separate all the training data sets. So for now, there is no noise. We'll introduce noise later. Then we will go to mean square error based like solution there, where you will minimize something else there. We bring some modifications to that. But for now, if you want me to write here also, no outliers, you could say. No outliers or noise. I could say there could be still some noise, but noise is such that it doesn't move or change from one party to the other party. It just could roam around there itself within this limit. Okay, these are the two assumptions. Now, let y be, so you first come up with some random, as one of you has mentioned, assume that I have come up, again, let us restrict to just a two-dimensional case. Assume that you have come up with some random line there. Then there are some misclassified feature vectors out there. Okay, let us define this y may contain all misclassified feature vectors. This is the set of all misclassified feature vectors. Now let us define a penalty term which takes into account all these misclassified voxels, and then we are going to modify this line such that this misclassified voxels will come down. That's the basic idea that we are going to follow. Okay. Now, how should we define a penalty? That's something we should now come up with a penalty term. That's what we need to do it. So before that, again, let's go back to, as I said, we will restrict to this term. Okay, now I'll not use this W naught anymore. This is what I would use. Let us say g of x bar, when I substitute this, for one class it would be greater than 0 and another class it is less than 0. So let us say that this g of x is greater than 0 for all x bar that belongs to omega 1. Okay, and similarly, of course, then what will happen? The consequence of that is less than 0, that is negative in other words. Okay, for all x bar that belong to omega 2. Clear so far? Now, let the function that we define here be j of what is our parameter here that you should change? What are the parameters for us? W. So I should write here my last function in terms of j of w bar. Okay, this is what I should write, last function. So maybe I will write the last function first, and let's see an intuition for that, followed by that. For all, I'm not sure if it stands in between. Okay, good. For all x bar that belong to y. So I'm considering this is my set of all misclassified voxels. For all x bar that belongs to this class, let me put here delta x, which I will explain shortly, times w bar transpose into x bar. Okay, I will illustrate that now in more detail. My j of w bar is equal to, for all x that belong to y, delta x times w bar transpose into x bar, where how is this delta x, delta subscript x is defined is -1 for all x bar that belong to omega 1 and +1 for all x bar that belong to omega 2. Are you able to make any sense out of this last function defined? Can one of you give it a try to explain what exactly are we doing with this last function?
Feature vector is wrongly classified into omega 1. is actually negative, but
Correct.
it is showing us positive.
Very good. Right. In other words, you are just summing up the value of g of x bar, absolute values of g of x bar for all misclassified oxels. That is all some fancy mathematical terms we have mentioned it. I could have even put their absolute, but later I want to take a derivative. So I don't want to look that ugly. Still, its ugliness is hidden. It's still there. It's not that there is derivative when you have absolute value as ill behaved, that is there, but looks good here. This is the common way in the textbook it is represented. For all, no, yeah, anyway here capital Y. So I am considering only those voxels here that belong to the misclassified voxels. Consider a voxel which originally belongs to class 1, but because of my random allocation of the line, it went to class 2. What will happen to my, delta x of naught. Okay, I myself felt that I have written a function here. It's not a function, delta x into w bar times x bar. Okay, so if something belonging to originally in the training set, ground truth tells you that it belongs to class 1, it went to class 2, this will be negative. I'm just making it positive here. This is based on training set. Okay, this is original actual ground truth. This is not what your algorithm has assigned, but rather this is based on your training data. Don't think that in your if your algorithm tells it belongs to omega 1, you keep minus. Okay, it's the other way around. You look at, these are all misclassified ones. This is where you look at the training data and you are doing it. In other words, in simple words, you are taking just absolute values of these things. With that, you could also notice here that it is also taking care of the Euclidean distance. If you recollect, do you remember the expression that we derived for R yesterday? R equal to absolute value of g of x bar over norm of w bar. So g of x bar is there here. So it further it is, right? This expression of omega bar transpose x bar will be high. Unless you correlate it with yesterday's intuition that are the geometry based intuition that we have did it, this might look all of a sudden coming out of the blues, but hope you are able to connect both, right? Well, now you got the last function. So typically, right. This is what I have mentioned here. So this is my assumption. Let g of x bar is positive for class 1 and negative for class 2. If I had switched them here, I should also switch it there. That's all. Minus plus. See, essentially keep in mind again, while if you are given and if you have to solve a problem, don't get confused. All, if you are in any doubt, what you need to do is simply compute w bar transpose into x bar. If it is a negative, look at what should be the delta x for that should be -1. If it is positive, it should be negative, so that you are always taking absolute values of errors. That's all. Is that clear? Good. This last function is there now. Then how do you typically, let me put it this way. You have, for example, you know the w bar value at t, you know it. Okay, t iteration, you know it. You want to do it at t plus 1th iteration, and this is your error. So did you also write this expression in the other course? Okay, you please, gradient descent also you have done there. Good. Then please tell me the expression. W bar of t plus 1 equal to minus, okay, any variable you could take. For me, let's say take rho t, some value which you could, if you want, can vary for each iteration. Okay, into, right, do j of omega bar by do, sorry, it's not omega bar, sorry for saying that, w bar. Okay, omega for us is omega 1 and omega 2, weights we are calling it as w. This algorithm is referred to as gradient descent. I'm sure in some of your mathematical courses also you would have come across this. Even if you did not come across, don't worry, this is a very simple thing. See, essentially, why not gradient ascent? Even if you don't understand, at least that question should come. There is a descent here. When do you ascend and when do you descend? When do you use gradient ascent? Assuming that exists, of course it exists. And the ascent to, that's all. So consider you have some curve like this. You want to find out a minimum, you go for gradient descent. Okay, and then here you go for a gradient ascent. All it varies is the sign here. When you are ascending, this will be plus, descending minus. Okay, and again here it's very easy to get geometrical interpretation also. So you yourself try it. Assume that here this is your function here. Okay, j of w bar, you have it. So there you essentially draw this. What will happen to that? And then in which direction you need to move, you just do it. You see any gradient descent, it will be, then you will be moving. This is in this direction. So minus and plus, you will you can correlate from that. If you want a geometrical interpretation, give it a try. Right. So all I need to now do is get this derivative again. One more time, let me insist here. What are the dimension? What is the dimensionality of dou j of w bar by dou w bar? Very good. So these are in fact L+1 derivatives. So that you be clear. Otherwise, all of a sudden it looks like scalar. So this is like the gradient that we discussed in image processing. Okay, this is equivalent to having a vector where this function, last function j, first element will be with respect to w1, w2, so on and so forth till wl and w0. Okay, hope keep that always in mind. Right. So can you now tell me the expression for dou j bar of w over dou w bar? What is the value there? So let me ask you to, for all x that belong to y, okay, you tell me, you write it, tell me now, what do I get there? Where is my j of w bar in the first place? This is my j of w bar. So you tell me now what would be the expression? Delta? Very good. Delta x into x bar. Very important thing again. Is everybody able to clearly see why you arrive at this derivative? Look at it. If that is not very intuitive to you or very obvious to you, think of writing it as w1 x1 plus w2 x2 so on plus wl xl plus w0, right? This is of dimension 1 here. Now your dou j by dou w bar, when you are doing it for the first element, of course there is this del x is there, minus or plus, that let it be there, you could do it. But then if you are taking derivative with respect to w1, what do you get there? x1. Very good. And so on, x1 plus x2 and so on, you will get it. Is that clear? I am taking derivative. So essentially, sorry, it is not x1 plus here. I'm sorry for that. That will be, yeah, delta x into x1, right? And so on, delta, let me call still x1, because anyway that is dependent on this x. Okay, so that xl and of course delta x here. So first time when that is, yeah.
The x1 values of all the misclassified data will be added, because we are taking summation for each vector.
Correct.
So
Yeah. 1 minute. Yeah, just a minute. You have a point. Yeah, this is for a single one, correct? Now the summation is there. Because of that, what you will get here, this will be, let me call it as first vector, maybe with the prime number there, with a superscript there. Then it could be x prime here. Let me write x2 bar. So if you look at, if you ignore the summation,
I think that also will come out to be a X1.
which one?
The first one.
This one.
Right. All will be the first element of the test. Not in this
No, I maybe let me just clarify this. See, ignore this for a moment. Okay. Then what will you get here? There is just x bar you will get. That means what you get there, these are all the values that you would get here, right? You will get x1. So this also you ignore, that's anyway change of sign. So x1, x2, so on, xl plus 1. That's all you will get. Now you are doing summation for different x values. Okay, that's why there is a summation here. Is that clear?
Yes, so that's why I'm saying that let's suppose misclassified data. So all of the first terms will be added in the first two.
Correct.
So it won't be del x1 plus del x2.
It will be because if the misclassification happens from class 1, you had -1 there. If misclassification happens from class 2, you have +1 there. So there will be del x1 here.
Yes, sir. That I'm not saying. I'm saying that the next term, the next summation term will be another x1 of the second vector.
Correct. That's right. So yeah, maybe just to have the confusion comes from this x bar can have different values. I have not used any index. So if you want, yeah, x1 I am using here. So let me put a superscript here. Assume that this is xi, right? All I have there is delta xi, or maybe delta xi into x1 bar plus delta x2 into x2 bar plus so on. Is this fine? No, this can have xi can be different values. This I is varying. Let's say there are some p points are there. So each one you hold the vector, you multiply and sum them up.
Column wise, it will be the same thing.
Correct. That will be column wise. It will be the same thing because it is for one vector. Either you take positive or negative, depending on whether it has been classified into misclassified from class 1 to class 2 or class 2 to class 1. Is that fine? Good. So I will remove this superscript. It is too many notations are coming, but I hope you understand that. Let me substitute that here. So that will give me W bar of t minus rho t into summation of, for all x that belong to the set of misclassified voxels, delta x into x bar. This is how we are going to update the weights. If you are updating the weights, obviously your plane is perpendicular to that. That relationship we have already seen. It is indeed, these are the weights that we are going to compute. Don't you see something unusual here? That there is in the whole term has nothing to do with weights. This whole term, what happened there? Will it be every time constant or what's going on here? Very good. They keep changing. This x bar that belongs to y, every time you come up with a updated decision plane, you need to relook at the misclassified feature vectors at that point of time, and based on that you are computing this. That point has to be very clear, that is there in it. Okay, but again, this is fine to calculate, but if you see in a strict mathematical sense, of course this absolute, if you have, and if you are taking a derivative at the transitions, the derivative is not defined, but that's all right. Here it is defined everywhere. When you come here, that maybe some abuse of mathematical property is there, but this works fine. It's fine for your practical purpose.
Sir, I have a question that,
yeah.
Is there any particular reason we are using the del x function? Like we could have gone with the absolute value function.
It is exactly absolute.
Because that would remove any ambiguity
in the writing. No, only thing is, if I had used absolute, when I take the derivative, I need to say it. The moment I write it as del x, I'm just bringing it here. See, f of x equal to absolute value of x is there. I need to write there derivative. If you ask me, derivative equal to 1 when x is greater than 0, minus 1 when x is less than 0. That's how I should write. Similarly, I should write this function also in the same way. So I should write two equations. Instead of that, that has been encoded here into delta x. That is the only difference. So it is no way different from taking an absolute value. Is that answering your question? Good. Right. So now it should be clear to you to an extent on how you are going to find decision planes. You start with a random initialization. There are different ways of doing it. Again, what we discuss, if you look at into the Theodotus textbook, or another classical textbook is Duda and Hart, the textbook, you will see and realize that we could spend the whole semester simply on linear classifiers, not even have to go to nonlinear classification. There are enough number of methods are there. So whatever we are discussing here will be a couple of basic methods we will discuss. Followed by that, we plan to go to at least one method which is kind of gives you state of the art or very popular or widely used. That's what we will do. So when I say some algorithm here, it's not that this is the only way to do it. Just keep in mind that we are just discussing one possible way. There is no reason why gradient descent only has to be used. There are other things, since we have to at least get a feel for it with one or two algorithms. That too, to get an intuition, we are doing with some basic algorithm. Okay. Yeah. So let's, since you may need to some point implement that, let's go into a bit more detail on how you do this. So let me write the algorithm here. Okay, so let me also write the equation here so that I don't have to every time put my head up until it takes. Okay, that's the equation there. Now, I would, for example, as you said, first you choose W bar of 0 randomly. Okay, then also you choose here, not only this, you could also choose, you don't call randomly for rho of theta. With some empirical reasoning, you would choose rho t here. Okay, and or you call it as rho naught. For most of the, again, this is again, as I said, I would put this in double quotes here. I'm sure if you look into the literature, there will be better ways than choosing it randomly. Okay, but we will go, for our class, we choose it randomly. Again, I say here, choose rho naught. But again, we are not going to discuss or consider any methods which also have some kind of empirical approach on how to choose rho naught. So if at all you have to implement it sometime in an efficient way, you should look how to choose these values also, although we wrote it randomly, if that convergence becomes a critical issue there. Okay, and of course you start with your t equal to 0, right? And then you do a set of steps here. What will you do? You first initialize your set to phi. So what is y? Y is the set of all misclassified feature vectors. You initialize it to phi, but phi means null here, okay, not another variable. Now I will vary for I equal to 1:n. So I have n samples or n feature vectors are there. For each of them, I will go through each of them. This is also going up. For each of them, what I will do is, if delta xi times w bar transpose times x bar is greater than, I don't know why I wrote it, but let me write it still. Then I do it as phi equal to y times union of xi bar. Okay, so basically you look if it is misclassified. Okay, don't you just decode it later. Otherwise, I need to spend time on that. So if it is misclassified, add it to set of y, which you started initially with a null space, null set. Okay, you keep adding them. Okay, and then find out y for a given w bar. Okay, and after that, what you do? You do w bar of t plus 1 equal to w bar of t minus rho t times that whole equation you could write here. For all x that belong to y, delta x times x bar. Okay, you find out the new estimate for this weights vector. After that, they have given it just rho t, but in the course we never do that. But let me write that. You somehow have a magical subroutine that updates you and gives a wonderful weight. So let me write rho t there. It just, then you do t plus plus. You are going for a next iteration there, and last line you do all these things. Next time if you want to do it, while you tell me what should I keep here. Yeah, tell me now. Y phi, it's not Wi-Fi. What I should see put in between? Equal to phi, greater than phi, not equal to phi. That's all. You repeat this first time you do while. I'm sure all of you are programmers, I think professional programmers, I hope. So you all know do while thing.
There is another assumption that there are no outliers.
That's right. That's the initial assumptions we have written. Otherwise, you go for least square algorithm kind of stuff, which also we plan to discuss. Okay, in the coming classes, we will discuss that. Here, the very assumption is noise can be there, but not to an extent but that it gets misclassified. Even despite noise, they are still in the boundaries. Okay, that's the whole thing. If you have to implement this, and probably you may get some exercise where you need to implement that. Any questions on the algorithm? Is the algorithm clear? Right. Well, if you want, I could give a geometric interpretation also on why this works when there is a misclassified one. Again, I'm afraid if I write, it will take 10-15 minutes and 10 minutes at least to do that. So please look into the theoreticist textbook. That's nice. If you have a, so essentially make a note here. This X bar is a misclassified oxel. So anyway, I'll draw something still. You have a misclassified oxels. Let's say this has to come here. So then you will add to the W bar. This would give you how much weight or scale you do to X bar. Consider there is only one X bar. This gives you with how much scaling you give. For example, this is like this. And now with what scaling you would add, and then essentially now your new W bar vector will change now, and that would essentially make it rotate. So I am not drawing it properly, but I hope you got some idea. And now please do go through the textbook and have it. This is nice to important to have some intuition geometrically as well. Just notice x bar, you give a scaling and add it. This is not every x bar comes here, only the misclassified vectors would come here. That's how you could see how this would rotate such that misclassified one will move from one class to the other. One more thing, there is yet another algorithm given in the textbook after this algorithm, where this update, if you look at it, this is nothing but a summation you are essentially doing here. On the other hand, you could also think of repeating this for each misclassified vector. Maybe I will make it a little more clear from this. I would update this not necessarily through summation, but every vector I keep moving it rather than taking summation at the end doing this. I could do it each feature vector, misclassified feature vector, I could update this thing. So that is another version. As I said, there are quite a lot of possibilities are there. Just to tell you that there are other possibilities also. Okay, but for our purpose, maybe if you solve problems, we will stick to this one. The example that was given again from the textbook is you randomly initialize the plane to be x1 plus x2 minus 0.5 is equal to 0. What all information can you tell from this? That tells you that your W bar is equal to, very good, 1, 1 minus 0.5. That's all you could get from here. Then, if you want, we can plot this also, how it looks like. Let this be my x1, let this be x2. Okay, let me put something in terms of 1/4. Okay, anyway, this line itself has become a polynomial by the time it came to the other end. Okay, so where does this have a point on x1? 0.5, right? x2 equal to 0 on this. This is 0.5. So let's consider this is my point here. What about on the x2 axis where this line will be there? Same thing, right? 0.5. Okay. Again, I wish I have a scale to draw here. Okay, this already went badly. That's okay. This is what I have. Now, this set of, you have a lot of points that have been correctly classified on one side here, and maybe on the other side here, you could have anywhere. It doesn't really matter. You could spread across. There were two misclassified vectors that were given. One is 0.4, 0.05, and the other is minus 0.2, 0.75. Okay, 0.4 somewhere here, 0.05. That means on the very border it has been given. So there is something here which should go to the other side of this line ideally, because this is misclassified. Another is minus 0.2. This is minus 0.25 somewhere here, and 0.75. My 0.75 is here. So somewhere in this region. Okay. So if I had got a line, so what ideally should happen now? My line should come, again, I don't know. I'm just drawing something, a line. where this moves, unless these other things we have to look at where the other points are there also. So how many possible lines can be drawn here? Infinite number can be drawn unless I tell you where these other points are there. So don't see any other points, okay, and then say that they are misclassified. This is a wonderful line that will respect all the earlier ones, but still will do the correct classification. Okay, so that's what you should end up with now. And given these 2 points, now calculate the new line. That is the problem given. Okay, please work it out. Not now, after you go, and come to the next class after working this out. Okay.